The Supply Chain Knowledge Assistant is designed to solve a specific enterprise problem, allowing users to query dense, complex supply chain data using simple natural language. When a user types a question, that text prompt begins a rapid journey through a highly structured digital environment, navigating multiple layers of logic before a response is ever generated. Deploying this at scale requires a multi-layered architecture to manage data integrity and user permissions. A basic script lacks the necessary controls to handle corporate workloads. The application functions as a full-stack system, integrating user login protocols, protected network routes, and encrypted conversation storage. This split-screen diagram highlights the difference. On the left is a naive prototype, a user connected directly to a large language model. On the right is a production architecture, placing a complex stack of dedicated services between the user and the AI. The basic model on the left operates entirely unprotected. It lacks security firewalls, memory retention, and corporate access controls. The enterprise model on the right introduces specific layers to protect API routes, manage user logins, and encrypt incoming data before the LLM ever sees it. To understand modern AI applications, developers must master system integration. Writing effective prompts is secondary to building the infrastructure that delivers those prompts securely. We are going to deconstruct this architecture entirely. We will trace the exact path of a single text prompt as it travels through all 5 distinct technologies in the stack. Enterprise AI requires a robust technical shell built around the core intelligence. It is a strict systems engineering challenge. The journey begins on the client side. Before a user can ask a question, the React frontend requires them to input their corporate credentials. This network map shows those credentials leaving the React client. They travel over the network and hit the FastAPI backend, which access the system's central orchestrator. FastAPI does not verify these credentials itself. Instead, it routes them to an external LDAP server, which serves as the corporate directory. The LDAP server checks the credentials. If they match an authorized employee, it fires a success signal back to the FastAPI orchestrator. Receiving that success signal, FastAPI mints a JSON Web Token, or JWT. This token is a cryptographic proof of identity. FastAPI sends this JWT back to the React client. The client will now attach this token to every future request to prove authorization. This handoff is a hard requirement. The AI backend will eventually search through internal supply chain documents, which must be strictly protected from public network access. Without this distinct access layer validating every user, the AI model serves as an open door directly into restricted corporate data. With identity established, the user submits their natural language question about the supply chain. The text prompt is bundled with the JWT and moves from the React frontend back to the FastAPI orchestrator. This diagram illustrates a primary architectural limitation of large language models: statelessness. The LLM processes a query, returns an answer, and then immediately wipes its memory banks clean. To solve this amnesia, the FastAPI orchestrator intercepts the incoming prompt. It takes on the responsibility of managing the conversation state externally. FastAPI duplicates the incoming text prompt. It routes one copy down to a designated Snowflake database node. Snowflake permanently logs the user's question. This provides strict auditability for IT and allows the user to pull up their historical chat sessions upon logging in. By forcing state persistence through Snowflake, the architecture transforms a forgetful AI endpoint into a continuous, reliable digital assistant. The prompt has been authenticated and recorded in the database, but it is still not cleared to interact with the language model. Users frequently type sensitive information into chat windows. If personally identifiable information or trade secrets are sent to an external AI model, it constitutes a massive data breach. This graphic demonstrates the scrubbing mechanism inside the FastAPI orchestrator. The prompt passes through a filter that detects sensitive data strings and instantly replaces them with asterisks. Only this newly sanitized text packet is allowed to proceed toward the external transmission phase. The entire pipeline is secured using AES encryption. This ensures the prompt remains protected while resting in the Snowflake database and while in transit across the network. The orchestration layer serves as a strict firewall. It stands between internal corporate users and the hosted AI environments. Implementing security orchestration is the mandatory tax developers must pay to deploy AI in a regulated enterprise setting safely. Finally, this sanitized, secure prompt exits the FastAPI layer and enters the Databricks backend. This diagram outlines the actual intelligence workload. Databricks takes the prompt, triggers a search query against a vector database, retrieves specific document fragments, and feeds them into the LLM. This process is known as Retrieval-Augmented Generation, or RAG. It ensures the model only relies on the highly specific supply chain documentation requested, rather than general internet data. The language model synthesizes those exact retrieved documents with the user's prompt, generating a final answer packet. The newly generated answer packet flows out of Databricks and returns to the FastAPI orchestrator. FastAPI takes the incoming answer and routes a copy directly into Snowflake. This permanently links the generated response to the original recorded question. The final response is routed back to the React UI, displaying the answer on the user's screen and completing the cycle. The intelligence of the system relies entirely on this pipeline. The output is the result of rigorous data retrieval and strict routing. This complete network graph displays the system we just traced. By zooming out, we can draw strict boundary boxes to separate the architecture into 4 distinct zones. Zone 1 is the React frontend, which is strictly responsible for managing user interaction. Zone 2 is the orchestrator layer. FastAPI, LDAP, and JWT handle all backend routing, logic, and access control. Zone 3 isolates the Snowflake database, dedicating it entirely to state persistence. Zone 4 is the Databricks pipeline, encapsulating the entire RAG retrieval and intelligence workload. This structure relies on system modularity. Each section is highly specialized and independent from the rest. Because of this modularity, engineering teams can swap out the underlying language model in Databricks without having to rewrite a single line of code in the React UI. Similarly, database engineers can update the Snowflake schema without breaking the LDAP authentication flow. Separating these concerns ensures that when something breaks, the team knows which zone holds the failure. It makes the system easier to debug, understand, and iterate on. Mapping the architecture this clearly empowers you to explain your own projects confidently in interviews, technical demos, and engineering documentation. In the upcoming videos, we will move past the high-level map. We will open the terminal and dive into the code powering each of these isolated layers. Success in enterprise AI depends on the security and efficiency of the surrounding environment. The architecture is what allows the prompt to function.